Hello everybody, and welcome to the next section, section 2.5, where today we're going to talk about the concept of continuity. Fair warning, this section will be quite a bit longer than the last section that dealt with the epsilon delta definition, but it should be a little more straightforward. It'll be longer in length, but it should be a little more straightforward in terms of the problem solving. It's a lot more math in this case, like the math you're used to. Not so much doing a whole bunch of, writing a paragraph about this epsilon delta stuff. Excuse me. All right, so let's get into it. Starting with our definition to kick things off. So when we talk about something being continuous, we want to be very clear about what we mean. And that is a function, f of x, is continuous at a number a if the limit as x goes to a of f of x is equal to f of a. So it's a nice short way of saying that f of x is continuous at a. And that's the way we would say that. In this case, if we do meet this criteria, the limit as x goes to a of f of x is the same thing as the value of f of a, then we would say that f is continuous at a. It's very important that we say at a. We don't want to say that, oh, f is continuous, because then we're saying that f is continuous everywhere, from negative infinity to positive infinity, and that may not be the case. Right? There may be an asymptote or some sort of it's a piecewise function. There's like a jump discontinuity, or there could be a hole in the graph if it's a rational function. So we do not want to get in trouble and say, yeah, f is continuous. Okay, well, f is continuous where? Right? Is it over a very large interval? Is it over all real numbers? Is it just in a very specific spot that it's continuous, and then in other places it's not because it jumps all around and has a bunch of holes and asymptotes? All right, so we start off by talking about continuity at a point, and that's what we're doing here in this first definition. Now, be pretty careful, because again, this is a pretty loaded statement. It's actually saying three things. It's saying that f of a is defined, meaning that a is in the domain of f. And that already right there is quite a lot to account for. We are saying that when we make this statement, f is continuous at a, we are saying that the function exists when you plug in this number a, say, x equals a, you plug that into the function, we are saying that that value is there. It's not a hole. It's not a vertical asymptote, right? We are saying, in a sense, that a is in the domain of our function f. That's already something quite important that we need to say. Again, like I said, this is a very loaded statement. It's also telling us more facts. It's telling us that the limit as x goes to a of f of x exists. Right? This isn't a situation where it does not exist. We're saying that we can find this limit, which means if the limit as x goes to a of f of x exists, that also implies that the left-hand limit exists and the right-hand limit exists, and both of those limits are equal. Right? That's the only way the limit exists, is if we get both the left and the right-hand limits to exist and have the same value, then we can say this exists. So even this itself is yet another loaded statement. And then, of course, what we're really saying is everything combined together. 1 and 2 combined finally give us 3. The limit as x goes to a of f of x. Well, we know it exists, and we know f of a exists. The third statement just says, if those two things are equal, then we have continuity. And be careful, because you can satisfy statement 1 and statement 2, yet fail statement 3. You may come across a situation where, and I'm just going to draw like a general function here, f of x, where maybe it has a hole, but where that hole is, this function could be defined as a piecewise function and say, oh, okay, well, when x is this very specific value a, you just fill in this point, and at any other point you go back to the function the way it is defined. You could see functions like that. They're not the nicest functions to deal with, but they exist, and we have to be able to handle functions that we come across when we see this. F of a is defined because there it is. Right? There's f of a. If I plug a into my function f of x, I immediately have to go to this point, not the point on the curve, because there's a hole there. So 1 is satisfied. 2 says the limit as x goes to a of f of x exists. That means I'm looking from the left and from the right, and that limit will be this value here. We'll call it L. And I just failed 3, because f of a is up here, which is a different number than the limit as x goes to a of f of x, because I compute the limit by computing the left limit and the right limit, and neither of those two tell me to jump up, and those two agree, so they are this value L. Whereas f of a is living out somewhere in space up here, away from my limit, so I lose this equality. So I don't want that. And you can kind of intuitively look at a picture like this and go, yeah, I don't think that's continuous, because there's a break, or there's a jump. And generally speaking, that's how that works. If you have to pick up your pen when you draw a function, if you ever have to pick up your pen, you have broken that, right? You've broken that function into pieces that are discontinuous now. Same thing with like a vertical asymptote. If I go like this, and then there's a second asymptote in the way, and then I go like this. Notice I had to pick up my pen in order to do that. So I lose that continuity. So in a sense, we don't want to see this and say that this is continuous at A. We really want to see f of a have the same value as L, so that my limit matches f of a. Now if I plug a into my function, I get this number L, and I have my equality. And also, again, of course, the left and the right limits agree. So that is what it means to be continuous at a point A. So let's play around with this concept a little bit and solidify it. So let's say we're given a function and they ask, is f of x equal to x squared plus 2 continuous at x equals 3? Let's say just based on that definition, in this case our a is 3, right? That's what we're going for here. And we just want to use the definition to show that it is, or maybe that it isn't. This is a nice polynomial, and polynomials are one of the nicest functions you'll ever come across because they are smooth and continuous over the entire real line. You could jump to a conclusion pretty quickly, but we want to show it. Right? We want to say, yes, and this is why. Right? That's good improv. You say yes, and. Right? You don't just go yes, because then people start raising their hands and they start asking why. Right? Tell me why. I want to know the truth. So what we want to do is look at those 3 criteria. Right? And I'm going to do them just based on the fact that first we want to know that f of, in this case, a is 3, f of 3 exists because 3 is in the domain of f of x equals x squared plus 2. Now, while we're here, we might as well go ahead and declare that f of 3 equals 3 squared plus 2, which is 9 plus 2, which is 11. So let's keep track of that. We now know f of 3. The second thing that we need to figure out is, the limit as x goes to, again, in our case, a is now a very specific number, 3. The limit as x goes to 3 of f of x exists. Why is that? Well, because it's a polynomial. But more importantly, I can declare that this limit exists because the limit as x goes to 3 from the left of f of x is equal to the limit as x goes to 3 from the left of x squared plus 2, which is equal to the limit, well, now we can just plug 3 in, right, at this point. And we can just plug 3 in pretty quickly. It's 11. And the limit as x goes to 3 from the right of f of x is the limit as x goes to 3 from the right of x squared plus 2. And again, we can plug in 3 and see what value it tends towards from the right-hand side of 3. And again, we get 3 squared plus 2, which is 9 plus 2, which is 11. And then we can say that the third part of the definition, to be continuous at A, says that 1 and 2 have to be equal. Right? And in this case, we have the limit as x goes to 3 of f of x is equal to 11, because the left-hand side limit is 11, the right-hand side limit is 11, thus the limit must be 11, which is also equal to f of 3. Right, so they're both equal. That means they equal each other, and that means I've satisfied 1, 2, and 3. Thus, by the definition, f of x equals x squared plus 2 is continuous at x equals 3. Right, and we're done. Right, so we just check and see that everything is satisfied, and that is the definition. It is these 3 things satisfied. So if we don't satisfy one of those things, then we don't have the definition, then we don't have continuity at A. Or if I don't check for these things specifically, then I have not shown that I have continuity at A. I have just guessed. And we don't want to guess. We want it to be a little more solid, right? So let's take a look at another one. This will be a rational function. Again, continuity is just this really, really nice property that we want. And we'll see that very quickly when we get into the next chapter and we start doing what's called differentiating, whatever that may be. When we start getting into that next chapter and we want to be able to differentiate something, right, we're really going to want to, have these nice functions with these nice properties. So this is a very desirable property for a function to have. So another example says, show that f of x equals 1 over x plus 1 is not continuous at x equals -1. So just like we can show that something is continuous, we can also show that something is not continuous. And the way to do that is to simply just show that it fails to fit the definition. One of those 3 criteria aren't met. That means I can't call it the definition that I was given. And you can already see that our A is -1 in this sense, and that is the vertical asymptote of this piece right here, right? X cannot equal -1. And they're trying to tell me to show them it's not continuous at X equals -1. Well, the quick way to do that is basically just look at that first property, which is, f of -1 has to exist, and we would want to find what that value is. But f of -1 is undefined. Right? You cannot plug -1 into this function to get 1 over 0, which is nonsense. So already we have failed the definition. Right? I didn't even get the first criteria. Does that mean I have to check the other? No, right? Because I've already failed the definition. Right? Thus, by definition, and if you fail the definition, then obviously you can just say it is not continuous. F of x equals 1 over x plus 1 is not continuous at x equals -1, right? Because it already failed the first criteria, because f of -1 is undefined. All right, so when it comes to functions that we'll look at in this class, again, being continuous is a very desirable property. We just don't always get it, but we know how to check for it. So there are different types of what we would call discontinuity. And when we say discontinuity, that just means, that's a fancy way of saying being not continuous, right? So there are different types of discontinuity. One of them is what is known as a jump discontinuity, or at least that's what I have heard it called. And what that looks like is something that we've actually probably come across several times already. We have this nice function, and then all of a sudden it jumps down here and decides to continue. Right? This is what we would call a jump discontinuity. This function cannot be continuous at whatever this red line is, a, because the limit on the left and the limit on the right aren't the same, so the limit doesn't exist. And that's one of the criteria we need for continuity. Since we fail to get that criteria of the limit existing, we fail to be continuous, we get discontinuity. So that's one way a function can be discontinuous. And we typically see stuff like this with piecewise functions. When we look at piecewise functions, they're defined by different pieces of who knows what other types of functions, and they're broken up everywhere. There's no guarantee that they're always going to meet together. They may have this jump. Another type of discontinuity is what we would call a removable discontinuity. And these aren't coming in any order or anything like that. And we'll use green. And that may happen when we have a function where if our function is coming in and then gives us a hole, but then continues. Right here we have a hole, and you'll notice that I had to pick up the pen. I mean, technically you could do this and then draw the circle and then kind of overlap on yourself, but functions aren't allowed to overlap on themselves. So even if I came in and started drawing the circle, at some point I would have to overlap that circle to get to the other side. I have basically failed to draw a function at that point because functions don't cross over themselves like that. So this is what we call a removable discontinuity. This happened with basically rational functions. Right? There may have been a time where we came across a rational function where it had the same factor top and bottom once we got it in factored form, and we could cancel out those like factors. Then we didn't have a full-blown vertical asymptote in that case. We just had a hole in the graph. So we call that a removable discontinuity because we can remove those factors and simplify that rational function. Again, that's not the only way to put a hole in the graph of a function, but that's probably the most common that we come across. And the other one is an infinite discontinuity, or at least that's one way I've heard it put. And that is when we come into a situation where we draw the graph of our function. Say it goes something like this. And then there's this like invisible line, this invisible vertical line that we do not cross. And then our function goes like that. Or something similar. This is where we have some sort of like infinite discontinuity, right? It goes down to negative infinity on this side and comes from positive infinity on that side. Or it may be negative infinity and then negative infinity on this side as well. That could also happen. And again, we see this when we come across, obviously, what looks like a vertical asymptote. And if we have this vertical asymptote in our way, we can never cross it. There's no way I can be continuous here. I've got to pick up the pen and start again. And again, like I said, even if I go, say up to positive infinity, and then there's a vertical asymptote, and then I come down from positive infinity and continue, I had to pick up my pen as I drew that graph from left to right. So they could be, positive infinity on both sides, or vice versa, negative infinity on both sides. But basically, when you see this vertical asymptote, you've got this discontinuity that you have to be wary of. And like I said, I'm not going to make you use this vocabulary, and I'm not going to say, identify which type of discontinuity. Really, the important thing is that there is a discontinuity. You could always go to the graph and justify which type of discontinuity it is. But those are the three most common that we see when it comes to dealing with the functions that we deal with. And be careful, because there could be some functions where, right now we're only looking at one point, a, when x is equal to a. But, take a look at something like the tangent function, for example. Right? That tangent function just has a bunch of these infinite discontinuities because it has an infinite number of vertical asymptotes. And that's just because that's the way the tangent function is defined. So it's not like it's going to be restricted to a finite number of discontinuities. There are some nasty, nasty functions out there that we've already seen that might have a lot of discontinuity. Okay, so let's extend that definition a little bit further into this one. A function, f, is continuous on an interval if it is continuous everywhere or at every point on that interval. I don't like just saying everywhere. If it is continuous, let's say at every number. There we go. Everywhere is a little vague. At every number a, and I won't even call it that. I'll just say at every number on the interval. And so it could take a lot of work to try and do this. If the interval is very large and there are an infinite number of numbers in that interval, do I really want to sit there and show it for every single number? I'll be there for the rest of my life and then some. And that's a bit too long in terms of trying to show it's continuous at each number, one number at a time. So again, think back to the definition. And the main thing was showing that f of a exists, but now we have to do it for an infinite number of a's. Part 2 said show that the limit exists. Well, now we need to calculate an infinite number of limits. And then we want to show that f of a is equal to the limit as x goes to a for every a, which is another infinite things that we have to show are equal. Well, there's a bit nicer of a way to do that. So here is an example where it asks us to show that the function f of x which is equal to 1 minus the square root of 1 minus x squared under the radical, is continuous on the interval and they give us a closed interval of -1 to 1. Hopefully we remember that notation. When you see the brackets, they're actually talking about the closed interval, -1 to 1. Well, we're stuck between these two numbers, -1 and +1. And look at what this function is having us deal with. It's a square root of 1 minus x squared. Right? That square root of 1 minus x squared, if we ignore the 1 minus part that comes in front of it, and we look at this, we're actually getting the upper half of a circle with radius 1. Right? And you can graph that on your calculator and see that. But then we get the negative in front of it, which means we're dealing with the lower half of the circle. And then we have a +1 constant, so it's been shifted up 1. It doesn't ask us to draw the graph. But if we were to draw the graph, we could go back and rely on some nice college algebra techniques to draw this graph, starting with the fact that this 1 minus x squared under the radical is going to give us an upper half circle. This negative multiple in front of it is going to give us a reflection about the x-axis. But then I have a +1 constant, not a -1 constant, but a +1 constant, which is going to shift it up 1 unit. So this will be a pretty cheap picture, but it'll show us. And again, we're only looking from -1 to +1. So I do get to use those endpoints when I graph my function. Maybe I can emphasize that. I do get to use those endpoints. They're not open circles, they are filled in circles. So we can see that between -1 and +1, right, this function does look to be continuous everywhere on that interval. That's just based on the looking at the graph. But that doesn't solidify it. That doesn't explain it quite well. We want to use the properties and the definitions to show this. So first, let's take a look at the limit as x goes to a of f of x. Well, maybe I'll get that if out of there. I don't even need that. So first, notice I'm picking just a generic a. I'm not saying, let's look at the limit as x goes to 0. Well, because then I'd have to do this whole problem again for when x is 0.1, and then when x is 0.2, and then 0.3, and then 0.31, and then 0.311111. There's an infinite number of numbers in that interval, so I don't want to attack it using specific values for a. I want to do it for a much more general a in that sense. So then now that means that we're looking at the limit as x goes to a of, here's my function given, 1 minus the square root of 1 minus x squared. And then using a couple nice limit laws, we can say that this is the same thing as the limit as x goes to a of 1 minus the limit as x goes to a of radical 1 minus x squared. So remember those limit laws that I listed out for you. It said if you have the limit of the difference of two functions, then you could look at the difference of the limit of those two functions. That was one of our limit law properties. And the limit of a constant is that constant. That was another nice property. The limit as x goes to some number of 1 has to be 1, because this is the constant function 1. That was yet another limit law. So I'm relying on some older stuff from previous sections here. And then again, we had another limit law that said, if we looked at the limit, right, ignore the minus because I'm going to be subtracting it anyway, focus on the limit as x goes to a of the square root of this polynomial function 1 minus x squared. Rather than do that, I can do the square root of the limit as x goes to a of the polynomial function 1 minus x squared. That was yet another limit law. Right? Instead of looking at the limit of the root, we can look at the root of the limit. Well, now I'm looking at 1 minus the square root of, I can evaluate the limit as x goes to a for every a when I look at 1 minus x squared, because this is just a binomial, 1 minus x squared, binomial, polynomial, then that means its domain is all real numbers. A is any real number in between this -1 and +1. Then that means that I can just plug a in here no matter what a is and get this weird thing, 1 minus a squared out of it. But it's still stuck under the radical. So what I've done is I've evaluated this limit, but I've evaluated this limit for all a's between -1 and +1. Right? If a is 0, I would just replace a with 0. If a was -1/2, I would just replace it with -1/2 and get my proper limit. If a was 0.99, I'd replace it with 0.99 and get my proper limit. Right? So I did it for all a's in that interval, but look at this and tell me what this actually is. 1 minus the square root of 1 minus a squared. Doesn't that look a lot like f of a, no matter what a I plug in? If I were to replace x with a in my function, what would I get? 1 minus radical 1 minus a squared. 1 minus radical 1 minus a squared. There's f of a. Now we just follow this argument, and the limit as x goes to a of f of x is equal to f of a. Well, by definition, that means that this function is continuous at a, but I showed it for every a between -1 and 1, because I didn't rely on a specific number between -1 and 1. I relied on a much more general a. Now I hand this argument to you and I say, pick whatever a you want. It's the exact same argument. Thus, f of x is continuous at x equals a for every number a on the interval -1 to 1, which means f of x is continuous on the interval -1 to 1. So again, you could even in this case plug in -1 here. Right? If I square -1, I get +1. 1 minus 1 is 0, radical 0. I still have 1 minus 0. That's 1. Right, so I can plug in these values of negative 1 on the endpoint and get the proper 1 out of it. And vice versa, if I plug in positive 1, 1 minus 1 squared, that's the same thing as 1 minus 1. That's 0. I still get the positive 1. I still get the endpoint. So it not only works for everything in between negative 1 and 1, it also works when it is negative 1 and when it is positive 1. Right, so when you're asked to prove that a function is continuous over an entire interval, you want a much more general strategy. You want a general A, and you want to show that it works for that general A in between, wherever your end points are, right? Your start and your finish. Okay. Moving right along. So now we've seen what it means to be continuous at a very specific A. We've extended that concept over an entire interval. The hope is to not have to do this for every single function that we come across. As a more general way of looking at things, I'm going to give you a couple theorems, and a couple in a row. All right, the nice thing is once we have a theorem, we can just roll with that theorem as long as things fit the criteria for that theorem. So this one says that if f of x and g of x are continuous at A, then the following functions are also continuous at A. And maybe we'll give them some numbers. Number one, f of x plus g of x. Let's go over here. Number two, f of x minus g of x. I guess I could have squeezed those both together, plus minus notation, but too late, no harm, no foul. Number three, f of x times g of x. And number four, f of x divided by g of x, provided g of x isn't 0, right? That would be weird. But then we'd be dividing by 0. And one more, I'm going to squeeze in there, c times f of x, where c is a constant. So c is just some constant multiple, right? It's basically just multiplying by some scalar. So if we know that f and g are both continuous at this point, then we can add or subtract or multiply or divide or even just multiply one of those functions by a multiple itself, and we'll still remain to be continuous at that point. And of course, we can extend this. If f and g are continuous over an interval, then we can add them and we'll still get continuity over that interval. We can subtract them, we'll still get continuity over that interval, etc., etc. So here's probably the first theorem that is the easiest to agree with, and the one that you'll fall in love with the most right off the bat. Theorem is all polynomial functions are continuous over the entire real line. Some people will say this a little faster by saying polynomials are continuous everywhere, right? But they are continuous over the entire real line, i.e. negative infinity to positive infinity, right? All real numbers. So that is a lovely thing about polynomials, and that's why it's one of the first types of functions we study, because they're so nice, because they're continuous everywhere. They don't have jumps or breaks or holes in them or anything weird like that. Right, so if I hand you a polynomial, before you even start thinking about trying to solve that problem, this better be in the back of your head somewhere going, ooh, Mr. Schaller just handed you a continuous function. Right? That's a good thing to know. Now, we do still have a lot of other functions that we've studied up to this point. Logarithmic functions, exponential functions, rational functions, trigonometric functions. So we want to also be able to kind of put those into a group, but we can't put them in the same group as polynomials. They're not that nice, but they're still really nice. They're really nice functions, but they're just not that simply stated. So I'm going to say the following functions, and this is a new theorem. I don't know if I stated that. New theorem. The following functions are continuous at every number in their domain. And be careful, some of these functions have different domains than others. So bring on the rest of the functions, right? Rational functions. Rational functions are continuous at every number in their domain. Basically, we want to watch out for a hole in the graph, like a removable discontinuity, or a vertical asymptote. That's where we'll fail to be continuous. But everywhere else, you'll see a nice smooth curve before and after that asymptote, or before and after that hole. Then we've got continuity there, because it's a nice smooth curve. Trig functions. Again, continuous at every number in their domains. So you have to know the domain of each trig function, right? The domain of y equals sine of x is negative infinity to positive infinity. You could plug anything you want into that argument for a sine function, because the sine function just oscillates. It's a nice smooth curve that never breaks or jumps or anything weird like that. So yeah, you could say that, yeah, well, the sine function is continuous everywhere. I could lump it in, with some nice polynomial functions. But when you say, okay, well, then the tangent function, oh, wait a minute, the tangent function has a lot of vertical asymptotes, right? There's a lot of discontinuities. And that's just based on the way we define the tangent function. It is the sine of x function divided by the cosine of x function. We have to look at that ratio. Now, if the cosine of x spits out 0 in the denominator, we've got a vertical asymptote. And trig functions are cyclical, meaning they have this repetitive pattern. So cosine is not just going to be 0 once and give you one problem spot. It's going to be 0 multiple times as you go through the real line, which means you're just going to keep getting an infinite number of discontinuities. So again, it depends on which trig function. And then we have to go to their domain and check out where they could be continuous and where those discontinuities could be. Root functions are continuous at every number in their domains. Again, think about like the square root function. It's defined for any x value greater than or equal to 0. But we don't want to plug a negative number into a square root function because we get some weird complex stuff out of it. So it's going to be, if it's a square root function, it's also going to be continuous from 0 out to infinity, with 0 included. But if you, all of a sudden you look at the cube root function, well, the cube root function has this nice shape to it. It goes all the way out to infinity, and it does truck all the way back to negative infinity, and there's no holes or breaks or anything. It is actually defined on the entire real line. Since the entire real line is the domain of the cube root function, now I can say that the cube root function is continuous everywhere. But as soon as I say the square root function, there's a massive restriction, right? We got to drop all those negative numbers. So it all depends on the domain of the function as to where you can talk about its continuity. Exponential functions. We should all remember what an exponential function looks like. It's just always increasing, stays above the x-axis, and it does have a domain of negative infinity to positive infinity, so we could say that this is continuous everywhere. And I'm not talking about introducing any sort of transformations or anything like that into this type of stuff, right? I'm just talking about like very strictly like y equals e to the x. I'm not talking about like shifting it up and shifting it down. So when I say an exponential function is strictly above the x-axis, that is without any sort of transformation. Right? Of course, I could shove it below the x-axis if I wanted to by just subtracting a constant. And then I have one more, logarithmic functions. The counterpart to exponential functions, or I should say the inverse of exponential functions. Now do be careful with log functions, because they have a heavily restricted domain, much like square root functions have a heavily restricted domain. Logarithmic functions, we don't want to end up plugging a 0 or a negative number into the argument of a log. That's not to say you can't do that. You would just get some really weird, complex valued stuff out of it. That's a little beyond the scope of this course. So yeah, if anyone ever tells you you can't plug a negative number into a log function, well, technically you can, and there are ways to evaluate that. But it's, again, beyond this stuff. That's you're getting into a very specific course on complex stuff there. I'll keep the lower two, and I'll just get rid of this top one. Throw one more theorem at you here. Well, not the last theorem, but just another theorem. I'll provide a quick example. And this one says that if f of x is continuous at b, and the limit as x goes to a of a different function g of x is equal to that b, then we get to say something really nice. The limit as x goes to a of f of g of x, which is the composition of f and g, notice we haven't mentioned that quite yet, is going to be equal to f of the limit as x goes to a of g of x. But we just saw that we need the criteria that this limit is b, and this is f of b. So this starts to introduce the notion of continuity when it comes to the composition of functions. And notice that we don't have to say, in brief, f of x is continuous at b, and g of x is continuous at b. All we need to show is that the limit as x goes to a of g of x is equal to b. And so when we're looking at this stuff, we're only concerned about this as a limit. Careful about limits. That means as x approaches a for g of x, we do get this value. But g of a might not necessarily even be there, right? Okay, now I'll give myself a little more space. So what does this theorem mean? Because this theorem's a bit different. This doesn't handle like a specific class of functions like polynomials or any of these. It talks about a technique for building a function like a composition of two functions, f and g. And I like this notation, f of g of x. I think I'll do this in a different color off to the side here. I like this notation, f of g of x. There's no doubt that g is getting plugged into f. But some people like this, what they call the fog notation, f of g of x. All right, so it looks like there's like f and then not a multiplication sign, but a circle and then a g. Hence why they call it the fog notation. It's not a O, it's not a 0, it's a circle. Why introduce that extra circle when it's just unnecessary? But both notations mean the same thing. But I like to stick to this notation. Okay, let's do an example here. Because this theorem's a bit different than just stating how to handle a class of functions and their continuity. This one's a little more specific. This one says, evaluate the limit as x goes to 1 of arcsine of 1 minus radical x over 1 minus x. I know, nasty looking at first, but it's quite simple. Trust me on this. We will get through it. But I definitely need a little more space. There we go. A little more space, and we'll be good. Remember that there's a notation. I think this is worth mentioning here. Arc sine of x is the same thing as saying sine inverse of x. All right, so this is the inverse sine function. I just want to be very clear about that. The book switches back and forth between arcsine and sine inverse notation. I guess it just depends whatever mood they were in that day when they wrote that section. But both notations are quite fine. There is a small danger when you deal with this notation, sine raised to the -1 of x. Some people think that, oh, that's just a -1 exponent. I'll bring it down to the denominator. That must be 1 over sine of x. Well, no, because that's cosecant of x, and cosecant of x is not the same thing as sine inverse of x. So it's its very own specific function. So yeah, we kind of, lazily borrowed this notation and reused it. So do be careful about that. But this is, the same meaning when it comes to arcsine. I am saying sine inverse. Or if I say sine inverse, I am saying arcsine. Arcsine is maybe a little more of an old school way of saying it. Okay, just want to be clear on that in case anyone forgot what that arc sine means. That means sine inverse. Well, great. Now let's take a look at this and see what happens. So if f of x is continuous at b, and the limit as x goes to a of g of x is equal to b, then we get to use this nice little manipulation in order to calculate that limit. So for us, our function f is going to be the sine inverse function, and our function g of x, in this case, is going to be this weird 1 minus square root of x over 1 minus x. All right, so we're going to have to manipulate it using this nice little technique that we got from the previous theorem. Right, and arcsine is a continuous function. Again, you can graph sine inverse on your calculator and take a look at it. Since we have that continuity, we can say that the limit as x goes to 1 of arcsine of 1 minus radical x over 1 minus x is equal to arcsine of the limit as x goes to 1 of 1 minus radical x over 1 minus x. All right, and I'll just say maybe off to the side, because y equals arc sine of x is a continuous function. So why didn't I just plug in the number 1 right off the bat? Well, 1 minus 1 is 0 up here, 1 minus 1 is 0 down here. That's 0 over 0. That's already nonsense. And then to try and find the sine inverse of nonsense would just provide more nonsense. So it's not going to help me if I just plug in 1. You can see there's an issue here. And I still have an issue. I still can't plug 1 into this function. 1's not in the domain of this function. I still get some 0 over 0. And the limit of x going to 1 of this function giving me 0 over 0 is telling me no news at all. Right? I can't make a conclusion there. But what I can do is play with this numerator and denominator. And this is a really neat trick because 1 minus the square root of x, I can look at the denominator as 1 minus the square root of x squared. You see what I did there? This is just x. If I square the square root of x, this is just x. These two have the exact same value. I'm not trying to play any tricks here. This is just x. Why did I rewrite it like this, though? Because now I have the difference of squares. 1 is a perfect square minus this square root of x is now a perfect square because I'm squaring it. So I've got a nice difference of squares. And I know how to factor the difference of squares. I'll get 1 plus radical x quantity times 1 minus radical x quantity. And try it. Try foiling this out. And if you're good with multiplying square roots together, you'll get right back to 1 minus x, which is exactly what we started with. Right? First times the first is 1. Inner and the outer terms will cancel each other both out. Square root of x times negative square root of x. That's negative square root of x squared. Radical kills the square. It's just minus x. But the reason I have to do this is to get rid of this 0 over 0 stuff killing my answer. Or I should say my solution. My answer is going to be fine once I get to it. So now I can look at arc sine of the limit as x goes to 1 of 1 over 1 plus radical x. Now I have no problem plugging 1 into this and evaluating this limit. So by plugging 1 in here, I'm getting 1 over 1 plus 1, which is just 1/2, which means my goal is to find arc sine of 1/2. So again, plugging 1 in, I'm adding 1 plus 1 in the denominator to get 2. So I got 1/2, but it's still inside the argument of the arc sine. So I don't want to leave it like this. I want to go ahead and try and evaluate what arc sine of 1/2 is. All right, so basically what this means is arc sine of some value is telling me my angle. All right, so that means that 1/2 is coming from sine of that angle. Remember, when you take the inverse sine or arc sine on both sides, it'll cancel out this sine and tell you the angle. So when I take sine of an angle, it returns a value. When I take the inverse trig function of that value, it spits back out the angle. And so it returns the angle for me. It's a bad circle. It's a better circle. And arc sine is defined between negative pi over 2 and pi over 2. Just need to remember that from our trig stuff, right? And we need to figure out sine of theta is 1/2. Well, it's only going to be positive 1/2 up in quadrant 1. And that's only going to happen when this is pi over 6. So there you go. I found my theta, which is arc sine of 1/2, because sine of pi over 6 is a half, sine inverse of a half must be pi over 6. And there's my limit. And so, trying to sprinkle in the trig here and there back again. Not too scary. We're at 1 hour. Ooh, right at the 1 hour mark. That's not too terrible. Like I said, this section is going to be a bit longer. There's just a bit more I want to say. And I have a couple practice problems that I want to do. So, another theorem. I think I've got two more theorems for you. This one says if g of x is continuous at a and f of x is continuous at g of a, then the composition f of g of x is continuous at a. Remember in the last one I said, we only had to look at the limit as x goes to a of g of x. Well, now we're saying, okay, what if g of a is defined and it does exist and it's perfectly fine? Well, this is a little bit more powerful stuff here, right? G of x is continuous at a. F of x is continuous at g of a. Why do I have to say g of a instead of some b? Well, this is technically going to give us some weird value b, right? Because I need to plug a into g first. It'll give me an output g of a, which I could then call b. Notice that b has to be plugged into f. Notice that g of a has to be plugged into f. So that's why we need to say g of a quite clearly there. All right, so we don't want f of x to be continuous at a. That's not going to work for us because we're not finding f of a. We want f of x to be continuous at the g of a because we're plugging in the g of a. All right, so these composition of functions stack like that. It's not good enough to say f is continuous at a and g is continuous at a, therefore f of g is continuous at a. That didn't work. Go back to the a couple theorems back where I told you that if f is continuous at a and g is continuous at a, then so is f plus g, so is f minus g, so is f times g, so is f divided by g, so is some constant times f. But I didn't say the composition, right? Because I only said f is continuous at a and g is continuous at a. I didn't use g of a to be plugged into f of g of x, right? So there was a reason we didn't get the composition continuity stuff back in that theorem. We needed to state it a little bit more differently in order to show that we do get that continuity for composition of functions. And here's a quick example. Nothing really to work out. I'm just going to simply state that, notice, f of x, let's do this. Y equals x, cosine of x squared is continuous everywhere. Right? just trying to think about that and as to why that might be. Right, we've got this composition of functions. So our f function is like the cosine function, and our x squared function is like our g function being plugged into the f function. So it's just like we're looking at a composition. In this case, g is in here. Now, no matter what a you pick, from negative infinity to positive infinity, this is a polynomial, and I know that polynomials, it's a power function, but that's still a polynomial, right? Y equals x squared. I know that this polynomial is continuous for every a in the real numbers, negative infinity to positive infinity, right? So I know that that inner function is going to be continuous everywhere. That means that this function g is continuous at every a. It's continuous everywhere. I've already met this first criteria for every a because it's a polynomial. And go back and look at that theorem that said polynomials are continuous everywhere. That means for every a. Now, the question is, provided I plug in some number here, a, will my f function be continuous at that g of a? Would it carry through once I found this g of a and have to then evaluate the entire thing? Would I get that my outer function f is continuous at that specific a that I pick? Yes, and in fact it'll work for every a because I can take cosine of any number. Why? Well, again, look at cosine, it's a continuous function. So no matter what x squared spits out, it's just going to be some real number, and the cosine function is defined for all real numbers because it's a nice smooth continuous graph. It's continuous everywhere, so it's going to give me an output. Thus, the composition is continuous everywhere. All right, so I finally get to state that this thing is continuous at a for every a. I can just show it for a general a and extend it to the entire real number line. All right, so again, composition of functions, when you look at them, you can't just jump from a to f of g of x. Right? You've got to go through the whole process. And sometimes I just like to draw this picture. Maybe it's worth a little refresh. I don't want to waste a whole bunch of time drawing a bunch of squiggles here. But I need to take some value a from the domain of g, and g is a function, so it maps this a to a value, a specific output, g of a. Then I can pick up that value and plug it in to my function f, and f maps that value to some output f of g of a. So this is how the composition of functions work. I start with some domain for g, unconcerned about f, and I find this codomain or this range for g. That output lives somewhere here. Now this range for g all of a sudden becomes the domain for this f of g of a. And then I take that value and map it through the function f. Never, ever, ever in mathematics, when we talk about the composition of functions, does it work like this. Right? Never, ever, ever, when we talk about the composition of functions, can I just jump from here to here, completely ignoring the space that I had to go through. I had to be very specific about going through all these outputs, g of a for every a, and then seeing if I can pick those up through f. And so I have to make sure that I go through every single space that I have to deal with. Can't make any illogical jumps. So that is a true composition of functions. One more. Again, not really problem solving here, but just want to say some things about, notice, y equals the natural log of the square root of x is continuous on 0 to infinity. So again, we have to be careful. The inner function is the square root function. And in the square root function, I could plug in the number 0, but the square root of 0 is 0, and log of 0 is undefined. And so for the blue, technically I could use 0 and plug any positive number in. But then when I start to go through this log function, I really do have to remove 0. It just doesn't make sense. Right? So here's a weird A. If A is 0, then I have to look and make sure, is G of A going to work and fit this criteria? Will G of x be continuous at A if A is 0? Well, if A is 0, I'm looking at log of 0. My G function is now undefined. So I don't even get the first criteria. So in order to talk about continuity, I'll remove that bad spot and just stick with 0 to infinity. Because the log function is defined for positive numbers, and if I plug a positive number in the square root, there will be a positive number sitting here that I can then take the log of that positive number and be just fine. So this is where I have to get rid of something in order to talk about a nice interval of continuity. Right? And it all just depends on the composition. Right? You can compose functions the other way and get yourself into a whole new messy situation. So composition of functions are a little trickier, right? The difficulty level is definitely turned up. That's a lot easier than just adding or subtracting two functions, or just multiplying two functions. Or composition is definitely something a little bit different we have to be careful about. And then I have one more theorem that I want to state, and that is the intermediate value theorem. And then actually later on in the course, we'll talk about something called the mean value theorem. And then there is something actually, if you want to be more specific, there's something called the Cauchy mean value theorem. But for now, we'll mention this and we'll look at a quick example. And then I have a few problems picked out. Hopefully they don't run too long. We'll see how many we can get done in a good reasonable amount of time. So mean value theorem states that suppose f of x is continuous on the closed interval a to b. Again, brackets for a closed interval. And let capital N, the book uses capital N, be any number. Between f of A and f of B, where we'll avoid f of A being equal to f of B. Lots of criteria to meet here. Already a lot of stuff we need to be careful about. Then there exists a number C in the open interval a to b such that f of C is equal to capital N. All right, so let me fix that N a little bit. There's a lot to unfold here. So this is what we call the intermediate value theorem. Right off the bat, we want to talk about a continuous function on a closed interval, meaning those endpoints are included. So that is very important. We want to pick a function. That function first must be continuous, and then it has to be continuous on an interval, and that interval must be closed. Then we want n to represent a number between f of a and f of b. Notice these are outputs, right? We're talking y values, not inputs on the interval a to b. And we don't want equality when we plug in the a and we plug in the b into our function. We don't want the same value, right? So that's another criteria we have to meet. Then there exists a number c in the open interval a to b. Notice it's an open interval now. We lost the endpoints, such that f of that specific c gives us this specific output n. So again, there's a lot to unfold here. I'm going to pick an interval a to b. Now this picture is not going to represent every type of situation you can come across, but it'll get us something to wrap our heads around. And then I'm going to pick, let's say f of a is this value right here, an output. And let's say this thing gives us an output f of b, maybe a little bit higher up here. Again, I have to meet this criteria that f of a and f of b are not the same output. So I'm going to make one of them larger than the other. Doesn't matter, it could go this way or it could go vice versa, right? It's not specific in the theorem which way it works, but I just want to give you a picture that works. So f of x has to be continuous on that closed interval. That's why I'm using those endpoints, and now I have to draw some sort of continuous function, and maybe it grows a little slowly, kind of dips, and then comes back up. Now, f of x could continue beyond that interval, and it could be continuous beyond that interval, or there could maybe be a hole in the graph over here. Who cares? We're not looking there. We're only looking on this closed interval, right? So check, f of x is continuous on that closed interval a to b. N has to be some sort of value between f of a and f of b. I'm just going to put it in a random spot. That is between f of a and f of b. Again, this could work if f of b is down here. It's still between f of a and f of b. It doesn't specifically say which one has to be the larger. And f of a is not equal to f of b. So yeah, check, 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 check. That whole first sentence fits my picture. Then there exists, this is an existential statement. It's saying somewhere out there, there's this weird number c on the open interval a to b, meaning it can't be the endpoints, right? You lose the endpoints here. But an existential statement stating that there must be some wacky number c out there in this open interval such that f of c provides me with this value n. There it is. There's that wacky number c. Right, and notice it's stuck in that open interval a to b. So it is in there because this is my closed interval from a all the way out to b. And c is definitely buried in there. So that's all the intermediate value theorem states. Let's look at an example that provides us with a specific function. said, we'll later get something called the mean value theorem. So you'll see this, you'll see problems like this actually pop up again, where we'll go hunting for this specific C. Here's an example that says, show that y equals x to the fourth plus x minus 3 has a root on the interval, open interval, 1 to 2. When you see this word root, we're talking a 0. Right? It's saying, hey, prove that this function has a 0 between 1 and 2. Now, this is a really nasty looking polynomial. It's degree 4. That could be really tricky, right? There's no really nice, fast way of factoring that. We're just kind of stuck with it as is. And we learned some techniques in pre-calc to kind of, try and find some zeros, like we had the rational zeros theorem that we could try and find. But that only helps you find possible rational zeros, meaning fractions. You could totally have a 0 that's a radical, right? And that list of possible rational zeros will leave you empty-handed. And so again, pre-calc's not a cure-all. It doesn't help us find every root. And the nice thing about this problem is it just says, show that it has a root. It doesn't tell you to find the root, right? It just says, show that it has a root on that interval. It could have more roots on that interval. It could have a very specific root on that interval, but it could be a really nasty number. So it's not asking us to declare that root x equals this nasty number. It's just saying, show that it must have one. So let's take a look. Our interval goes from 1 to 2. F of 1 is going to be 1 to the fourth plus 1 minus 3, which is 1 plus 1 minus 3. 2 minus 3 is negative 1. This, in a sense, is me plugging down f of a. F of 2 is 2 to the fourth plus 2 minus 3, which is 16 plus 2, which is 18, minus 3 is 15. Again, order of operations, right? Always, always, always. That, in me, is a sense finding f of b. Now notice what's happening, and I'm just going to give you a rough sketch here. From 1 to 2, that is my interval that I'm dealing with. From 1 to 2. I am first getting an output value of negative 1. Right? So I am living somewhere down here. Then when I look at b, which is 2, and I find f of b, which is 15, I know that I'm living somewhere up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. When I plug in 2, I get 15. Now here's my arguing. Because y equals x to the fourth plus x minus 3 is a polynomial, it must be continuous on the closed interval 1 to 2. Open interval 1 to 2 is actually good enough to get the job done. But we found that it has those endpoints, so might as well state that it actually works on the closed interval. And of course it states beyond that, but we don't need to go beyond that. So because it's a polynomial, it must be continuous. Thus, y equals x to the fourth plus x minus 3 must cross the x-axis between x equals 1 and x equals 2. My function y has to go from this point to this point. And aha, I just found my root. Now my function could stay down here and then cross, or it could cross really quickly, or it could cross a bunch of times and then land on that endpoint. Where is that? I don't care. Are there more than that? I don't care. Because I answered their question, because I crossed the x-axis, I found a 0, aka a root, and I summarized by saying, thus, y equals x to the 4th plus x minus 3 has a root on the interval 1 to 2. Job's finished. So again, I don't specifically care what that number is, whether it's closer to the 1 or closer to the 2, I don't care. Whether it crosses several times. Right? Now, obviously, I could do some process of eliminating, looking at that degree. At most, this function has 3 turning points. At most, I could, cross, hit one turn, cross again. There's my second turn, cross again. I could pick up another one. Right? But don't care. Question is answered, as far as they want it answered. So now, in this problem, they didn't ask for a general C. They asked for a very specific output. They wanted n to be 0. When they said root, back in the theorem, they meant you need to find me a value between f of a and f of b, and that value needs to be n equals 0. It needs to have 0 output. It needs to be a root. What that C is, I'll leave that to you. Try and find that C. Go ahead. It may not be that hard. Or it may be rather difficult. Maybe the only way to find that actual C, and this is probably why they did not ask, is by doing a bunch of numerical approximations, which is rather tedious. And obviously not worth it in this case. But if you feel like you need a challenge, be my guest. Don't waste time on it, though. Okay, where are we at? 1 hour and 28. Okay, yeah, like I said, this one will be a little lengthy because I do want to hit some problems. Let's first take a look at this one. Which says, explain why the function f of x equals, and it's going to be a piecewise function, x plus 3 for x less than or equal to negative 1, and 2 to the x for x greater than 1, is discontinuous at a equals negative 1. It then asks to sketch a graph of f of x. So the graph will be very helpful to show us the discontinuity. That's really why they're asking you to do that. You should be pretty comfortable graphing piecewise functions, but if you're still a little shaky or a little rusty, I'm going to go ahead and graph it for you because I think it's going to be a good review. So we want to explain why this function is discontinuous, that is not continuous at this value, -1. And you'll notice that, oh, sorry, I forgot my negative right here. There we go. So we'll notice that for this piecewise function, if we're dealing with values less than or equal to -1, we use this linear function. If we're dealing with values greater than -1, we're using this 2 to the x exponential function. First of all, the limit as x goes to -1 from the left of f of x. Remember, we're talking about continuity, and there are those three things that we need to satisfy for continuity. So if we can show that the limit fails to exist, we can show discontinuity. We can't show that f of -1 doesn't exist, because it does. When we plug the number -1 in, we plug it into the first function and we get an output of 2. So we can't go about showing it with that one. Maybe we can show it with the first property that, or sorry, not the first property, the second property that talks about the limit. If we can show the limit fails, which, how do we show a limit fails? We show the left and the right limit aren't the same, then we're good to go and we've got discontinuity. This is the limit as x goes to -1 from the left. Since I'm coming from the left, I must use the first piece of the piecewise function, because only that piece is defined for values to the left of -1. And if I'm coming from the left, then I use that x plus 3. Now I can plug -1 into this and show that that's my left-hand side limit. The limit as x goes to -1 from the right of f of x is going to be the limit as x goes to -1 from the right of 2 to the x, because I'm coming from the right of -1. That is, I am coming from values x that are larger than -1, and the piecewise function tells me which piece to use. That is the exponential part, 2 to the x, which is 2 to the -1. Again, I'm just plugging -1 in for x. This is a negative power, so this is really 2 to the first power downstairs, which is 2 downstairs, which is 1 over 2. The left-hand limit and right-hand limit are not the same. Thus, the limit as x goes to -1 of f of x does not exist. Since the left and the right limit don't agree, the limit does not exist. Since the limit does not exist, therefore, f of x fails the definition. F of x is not continuous at a equal -1. Not continuous, the same thing as saying discontinuous, right? So we go about by looking at the definition of continuity and showing that it fails to live up to the definition. Now it asks us to sketch a graph. And again, that word sketch means it obviously does not have to be perfect here. It's broken up at -1. So let's go -3 to +3 on our graph. That'll be good enough. If I graph this linear function x plus 3, say 1, 2, 3, 4. Oh, I wish I had a little more space, but I'm going to graph the first piece x plus 3, and I'm going to graph it in blue, which is the linear function that has a slope of 1 crossing through +3 on the y-axis. So I'm going to come from that 3, I'm going to go up 1 and over 1. Or I'm going to go down 1 and to the left 1. Down 1 to the left 1. My scale's a little off here. Maybe I'll move that 2 in closer. I tried to get things to fit better. Just to get a slightly better scale here. Square this up. Down one to the left one, down one to the left one, down one to the left one, etc., etc., etc. But I only want to draw it from here to here. Yes, I know this would cross through 3 on the y-axis, but I can't graph this linear function for values of x greater than -1. I must stop, and it is less than or equal to, which means I fill that circle in right there. I can't graph the rest of it because it is not the entire linear function. This piecewise function tells me to stop using x plus 3 as soon as x gets to -1. And then it tells me, now use the other piece. Now use 2 to the x for everything greater than -1. Not for -1, but only things larger than -1. Well, if I plug 2 to the -1 in here, it would spit me down at 1/2, which would be right here. But again, I can't use that because I don't have greater than or equal to, but I know it's going to start from there if I could use it, and then behave like an exponential function. If I plugged 0 into here, 2 to the 0 is 1. If I plug 1 into that exponential function, 2 to the 1 is 2. If I plug 2 into that exponential function, 2 squared is 4, etc., etc. You can start to see the trend of that exponential function. And there it is. Voila. Not continuous. We got a big old jump discontinuity. Not continuous. All right, so going back and using that early definition of showing whether or not a function is continuous or not. Let's see, for the sake of not making this too long, I might skip one of these. Let's do it. You can always pause it and come back to it a little later. Better to have more examples than less examples, right? So let's do it. So this video may be a little long, but feel free to break it up into 2 chunks. Let's take a look at this one. Says use continuity to evaluate the limit as x goes to pi of sine of x plus sine of x. So we want to try and use this fact that all of these functions have built-in continuity, right? The sine function is continuous everywhere. This sine function is continuous everywhere. Y equals x is continuous everywhere. So then adding these 2 continuous functions, x plus sine of x is continuous everywhere. Taking the composition of 2 continuous everywhere functions is continuous everywhere. So when it says use continuity to evaluate this limit, it's basically saying, hey, here's your free pass. There's a bunch of continuous functions. That means everything is continuous. Start evaluating it using all your nice limit properties. So when I look at this one, it's not too terrible. Yes, you could just plug in pi, but I'm going to look at the limit as x goes to pi of sine of x plus sine of x, and show you that I'm really plugging this pi into this function here, and then waiting and holding off on this sine function a bit later. I have to figure out what that sine of that value is going to be, which basically tells me to say we're going to evaluate first the limit as x goes to pi of x plus sine of x. Well, that's going to be pi plus sine of pi. So now I'm evaluating that limit, and since this is just one nice big continuous everywhere function. That means I can plug in that number pi, since it's in the domain of x plus sine of x, and just see what I get out of it. This is sine times pi plus sine of pi is 0. Right? Remember what we're dealing with. Pi is over here, and sine of that value is going to be 0. So this is telling me to evaluate sine of pi, which, wow, that's hard to do. I already did it. Ditto. Still 0. Yeah, definitely got to erase that. So again, not a terrible limit. Uses a weird composition of some functions and some addition of some functions, things like that. But still, limits are pretty easy. Next. Let's say we want to find the numbers at which f is discontinuous. It does also ask to sketch the graph, but it's a piecewise function. I know you know how to sketch the graph. Well, we'll still do it. Why not? All right, so they give you a piecewise function of f of x is equal to x squared if x is strictly less than -1, x if x is between -1 and +1, where it could be also equal to -1, and 1 over x when x is greater than or equal to +1. So it does want us to find all the numbers for which this function will be discontinuous. Well, we can see that x squared is a nice polynomial, so it's going to be continuous everywhere, but it stops when we hit this -1. So that is probably going to be our first problem, -1. X is continuous everywhere, it's just that straight line y equals x, but it stops at -1 on the left and stops at +1 on the right. So these are going to be our bad spots, -1 and 1. And then, of course, this one as well. Y equals 1 over x is almost continuous everywhere. It's just not continuous at 0 because of the asymptote, but we don't even get to draw this function there. We're away from 0. We don't even start drawing this function until we get to +1. So on this interval, 1 to infinity, this is continuous everywhere on 1 to infinity. So it looks like -1 and +1 will be our issues. And again, to show discontinuity, we can look at these. They are defined for -1 and +1, which means we're specifically concerned about these limits. Right? Where are we going to have discontinuity? It's basically going to come from the limits. So again, let's look at the limit as x goes to -1 from the left of f of x, which means we're looking at the limit as x goes to -1 from the left of x squared. We use the first piece because we're coming from the left of -1, which means I plug in -1 and square it and get +1. Now that was the left-hand limit around -1. Let's look at the right-hand limit around -1 and see if it agrees. The limit as x goes to -1 from the right of f of x is equal to the limit as x goes to -1 from the right of, I must use x, because I'm coming slightly larger than -1, which means I've got to go through this piece, x. So I plug in -1. Right away, you can see that those don't agree. So the limit as x goes to 1 of f of x does not exist. Thus, f of x is discontinuous. It fails to meet the definition of continuity at x equals -1. So that's what we wanted to find, but we're not quite finished yet because there's no guarantee that it's continuous at +1. It might also have another point of discontinuity at +1, so we want to check that as well. So let's do that. And it's the exact same process. Right, just repeat. But this time look at the limit as x goes to +1 from the left of f of x. Which means I'm looking at the limit as x goes to +1 from the left. Since I'm looking at +1 from the left, I'm slightly under 1, which means I'm still using x. So I'm plugging in +1 for x and getting +1 out of it. Let's look at the limit as x goes to +1 from the right of f of x, which means I'm looking at the limit as x goes to +1 from the right. Now I'm coming in from the right of +1. That's values larger than +1. I'm going to use 1 over x. But 1 is in the domain of 1 over x, so I can plug 1 in. I get 1 over 1, which is exactly 1. Aha, these two are the same. So I know that f of x is going to have a limit that exists there. F of 1 is going to be 1, because I would plug it in right here and get 1 over 1, which is the same thing I got here. So the limit's 1, the value f of 1 is 1, which means everything is okay when x is equal to 1. So I don't really care about that. It's only at x equals -1 where I have this discontinuity. So it's just this one value, -1. The +1 worked out just fine. And again, it only asks for discontinuity, so that's why I only gave them the discontinuity. Don't really need to say much more about this. You could summarize and say that f is continuous at 1. We want discontinuous. We got here, almost at an hour and 50. I think maybe I'll just pick and choose which one of these two is a little different. Yeah, and 45 is not too terribly far from 41 or the other one I did. So let's pick on, I liked this one, 47, that I saw out of the textbook. It actually asks us to suppose that f and g are continuous functions such that g of 2 is equal to 6 and the limit as x goes to 2 of 3 times f of x plus f of x times g of x is equal to 36. Find f of 2. Actually quite a neat little problem, just using a bunch of limit laws to get the job done. So let's do it. Right off the bat, we know these f and g functions are continuous. When they say that, they mean they are continuous, no matter where you look, which is nice. We'll use that to our advantage. 36 is actually the value of this limit as x goes to 2 of 3 times f of x plus f of x times g of x. All that stuff, when they evaluate that limit without even knowing what these f and g functions really are explicitly, they only know that the limit is 36 when they do evaluate that big limit, regardless of whatever those functions are. So I can play around with some limit properties and look at the limit as x goes to 2 of 3 times f of x plus the limit as x goes to 2 of f of x times g of x. All right, thanks to all this lovely continuity, I can just use all these nice limit properties, and rather than looking at the limit at the sum, I can look at the sum of the limits. Well, now I have a constant multiple 3. I have limit properties that say I'm allowed to pull out that constant multiple of 3. Again, lovely continuity between these two functions f and g at x equals 2, or I should say as x approaches 2. So I have some nice limit properties that say rather than look at the limit as x goes to 2 of f times g, I can look at, instead of the limit of the product, I can look at the product of the limits. Well, this is nice because this gives me 3 of these limits as x goes to 2 of f of x plus the limit as x goes to 2 of f of x times notice we have the limit as x goes to 2 of g of x. That was something that was given to us, but they said it differently. We know that the limit exists as x goes to 2 for g of x, but we also know that g is continuous, which means that if this limit exists and it is a continuous function, by the definition of a continuous function, this limit and this value g of 2 must be the same. By definition of continuity, the limit as x goes to 2 for g must be the same thing as g of 2. So this is 6. Notice that if I lose this word continuous, then I can't say that. I can't say that if I lose that word continuous, because the limit is not the same thing as the value of the function at a point. But because that word continuous is there, the problem is over the speed bump, ready to be solved. That's a constant multiple 6. I'm just going to write it out front so that I have 3 times the limit as x goes to 2 of f of x, plus 6 of those limits x goes to 2 of f of x, which means I have 9 of those limits x goes to 2 f of x. I'm just counting up how many I have. I have 3 of these limits to calculate, plus 6 of these limits to calculate. That means I have in total 9 of these limits to calculate. So I'll just rewrite it with that nice multiple out there. Now, all the meanwhile, this was 36. That never changed. This was always 36. I always knew that that big complicated limit on the right-hand side was going to work out to be 36. And we're home free once we divide by this multiple 9. Cancel, cancel. So now we're looking at 36 divided by 9, which is 4, to give us the limit as x goes to 2 of f of x. All right, thus, the limit as x goes to 2 of f of x is equal to 36 over 9, which is 4. And that's what we wanted to show. We wanted to make sure we find f of 2. But this is only the limit as x goes to 2 of f of x. I've got to play this game one last time. There's my limit and I have continuity for f, therefore I can conclude f of 2 is equal to 4. Since the limit as x goes to 2 of f of x is 4, thus f of 2 is 4. All right, so yes, the notation is different, but these are saying two very different things. The reason I can make that one last final jump is because it's continuous. And if it's continuous, then the limit and the value are the same, and voila, I've finally gotten to my value f of 2, which is 4. Okay, sorry for the big long section. It is what it is. But you can break it up into some chunks if you want, but I want to make sure I keep each video to section heading because I think that'll just work out a little better. Whereas in maybe in a face-to-face class, I'd get about well, it is the summertime, so our classes would be extended to quite a length, about 2 hours apiece. So, yeah, make sure you're practicing the definitions. Make sure you're practicing those theorems that you got and working on some of the problems, either out of the book or in the study guide, or if you have another book or somewhere to look them up, look them up. But this section needs some practice. There's quite a bit going on, and you need to understand why it's going on. So yeah, I will see you in section 2.6, where we'll jump back into some more limit stuff and looking at limits at infinity. So thank you very much, and I'll see you in the next section.